All right, well, we're going to get this Hangout session started now. I want to welcome everybody for joining. Today we're going to be talking about turbulence models. I'm trying to keep it at a very introductory level. We're not going to be going into any equations or anything like that. Again, my name is Roy Sable. I've probably talked to many of you on the phone throughout the years, product support specialist within Autodesk. Just as a reminder, this is our 5th Hangout. We've had 4 Hangouts so far, as you can see on the left of this slide. And the most popular so far has been our What's New within 2015. As you can see, 632 views within YouTube just over the past few weeks. That's been great. And if you are looking for these videos, they're in the Autodesk Sim 360 YouTube channel. So for those new to our Hangouts, I just want to remind everybody, what these are about. Pretty much it's somebody within Autodesk or maybe a guest speaker that will present some sort of material for 20 to 30 minutes. And then after that point, you're welcome to ask any sort of question. You're actually welcome to ask questions throughout the entire presentation, and there should be a question box within the GoToWebinar application, which will allow you to ask questions. We have multiple people from our team, from support and sales, sitting there waiting to answer your questions. For today's agenda, we're going to be talking about, of course, turbulence. And we'll be quick discussion about what turbulence is, followed by how it's modeled inside of software. And then I just wanted to present a general timeline just to give people an understanding of the scope of turbulence models. And then followed, we'll go over 4 of our primary turbulence models. Lastly, some notes and best practices. So what is turbulence? Turbulence is a violent or unsteady movement of fluid. If you were to look at the picture in the lower left-hand corner here, you can see it's just classic flow over a flat plate. The velocity profile is very even, going up to the leading edge, and then as it starts moving across the edge, eventually the flow becomes more and more turbulent. And basically what the turbulence is a eddy or circular movement of that flow throughout the flow domain. On the right-hand side, you can see more of what a real flow pattern would look like over a backwards facing step where the flow is very chaotic. It's not what we normally see inside of a CFD software where it's a very smooth velocity profile from one end to the other. And in terms of how turbulence is modeled in CFD software, in application, in an industry use, there's really 3 means plus a 4th, which is more of a academic study of turbulence. So from the top down, we have our classic flow averaging, which is the Reynolds averaged Navier-Stokes approach, which basically is averaging all those circular eddies to get a very smooth profile. And typically those eddies are assumed to be an equal length scale. So if we look at our picture in the lower right-hand corner, you can see we have these larger eddies followed by smaller eddies that kind of circulate within each other. And really, you wouldn't see any of those flow patterns within, for the most part, within a flow averaged analysis. From there, we get into more of a large eddy simulation. And at this point, you're going to be actually solving and visualizing those larger circular flow patterns in this picture. But the smaller eddies really are modeled within the equations. And the effect of the turbulence is captured, but the flow is not really shown. Lastly, we get into more of a hybrid of those 2 approaches, which we'll be talking about later. Generally, they're discussed as a detached eddy simulation. So here the LES modeling approach is used where it needs to be, while the flow averaging technique is used throughout the rest of the domain. So if you think of a flow over a cylinder, for instance, that wake pattern can have very large eddies. So in that region you'd get the LES approach, but upstream to that you get more of the flow averaging approach, where this will help with solver performance. Lastly, we have our direct numerical simulation. We don't have any technique like that within our own software, but really this is coming down to you're not modeling turbulence at all, and you're having such a fine mesh that you capture all the different scales of turbulence within the flow domain. Lastly, a lot of these different techniques take advantage of what are called wall functions, and we'll be talking about that more later. In terms of turbulence models throughout time, this is something I did quick research last week. So these are very general timeline. When you were to look at certain models, they have a large history just within that model and how they tweak it and tune it to different techniques or different deficiencies with that model. So if you were to go back way in time, late 1800s is really when Eddy viscosity, which is how we really describe turbulence, really started within academia. So that's just a basic concept. Now, when we start going across this timeline, anything above the timeline is actually a modeling technique that we have within the software. Anything below are ones that I hear about within support when people ask, why don't you have this technique? And I decided to just put them in there within that timeline to let you know where that came in place. So other ones that we have that we leverage a lot, of course, are the mixing length, K-epsilon, and then more recently, the Mentor K-omega SST approach, which really then drives into the later modeling down the road. So when you look at sort of the vertical scale, I tried to emphasize, in my opinion, what people use the most or should use the most when they're doing their models. So K-epsilon and Mentor, I've kind of labeled side by side. Depending on who you talk to, some people will say, well, the K-omega SST approach is becoming more superior. Maybe that should be more of an industry default. Don't really want to get in that conversation too much, but I wanted to emphasize that this is a very growing modeling technique. Outside of that, mixing length is a very simple modeling technique where really it's just changing your viscosity, for instance, just along the wall. Everywhere else is really just a constant value of viscosity. So in terms of the range here, just notice how we're starting in 1887 and progressing all the way to the early 2000s, while the K-epsilon is in the mid-70s where it really started to grow. And the later models are really trying to attack the deficiencies that K-epsilon really had. So in terms of K-epsilon, this is a two-equation linear eddy viscosity Reynolds average Navier-Stokes approach. So what it really does is it tries to model the turbulence throughout the flow domain where it effectively changes the viscosity and conductivity based on what the turbulence would change with inside the flow domain. Okay, hopefully that made sense. But either way, this is a classic approach. It's shown to be very robust within the industry, so it's got a long industrial benchmarking that you probably have at your office within your own model domain sets. And that's really the pros of this model. It's robust, it's proven to work, and has very low mesh requirements compared to the newer modeling techniques. Now, the K-epsilon model itself does have quite a few deficiencies, which will have been addressed in many current modeling techniques. Large adverse pressure gradients, which go along with predicting separation points, has always been one of the biggest cons of this modeling technique. So when I say large adverse pressure gradients, all that really means is if you were to think about a flow profile going over a wing, eventually that will separate, typically. And where that separation occurs, you start getting some backflow going along the wing wall surface itself, basically against the primary flow direction. And then you have the primary flow going over that section. So that forward and back movement is where this adverse pressure gradient occurs. And K-epsilon generally does not do a good job to capture that. Other aspects that are negatives that I see a lot of is mesh sensitivity. If you ever had a case with myself or Apollo and you're trying to model just a straight tube, we start talking about this conversation about K-epsilon and how you need to really monitor different wall function concepts. Now we start talking about wall functions. This is something that you don't normally think about. And most industrial models you don't need to think about. But when you're trying to really grow your CFD knowledge base, the law of the wall becomes important when you're trying to implement these different turbulence models, and your model is very sensitive to what is going on along the wall. So the law of the wall, which is implemented on K-epsilon, is valid in certain ranges. So if you look at this flow profile, as we looked at before, I overlaid a basic mesh, and this is not to scale at all, it's just trying to capture what's going on. These purple lines are trying to show those 3 boundary layer elements along the wall. The Y plus is really defining where that first element is located in the flow profile going away from that wall. And that first node is only valid within the equations for a specific range. You don't want it too small, because that's going to mean that viscous boundary layer along the wall. You don't want it too large, because really at that point you're getting into the larger turbulent region away from the wall. So in terms of the Y plus, when you're using the standard classic wall function, you really want that Y plus between about 35 and 350. And generally I like to be on that lower end when you really start to get to accuracy. Okay. Now, one thing that's actually newer within our software is something called a scalable wall function. It is something that's been around within industry for a while, but something we've recently implemented. And this is really to address a few deficiencies. So when we're talking about the wall function with the Y plus aspect, there's a min and a max, 35 to 350. So really, as you start refining your mesh, what happens is your Y plus starts dropping below that 35 value. Maybe it starts dropping below 10 or 5, and this is where you really start potentially impacting your accuracy of your solution, assuming that your pressure drop is really based on the skin drag along the wall. So if you're doing an electronics model, for instance, yes, Apollo?
Yeah, one quick item. I'm getting a handful of questions.
Sure.
There are some people that have answered the poll questions, but they're still not seeing updated slides.
Really?
Yeah, so I don't know how many people are actually experiencing that. If you don't mind, for everybody that's on the call, if you are still on the quick poll slide, feel free to shoot a question in or raise your hand. Most people should be seeing the scalable wall function slide, so I'm not exactly sure why. Okay, so I'm getting a couple stating that slides are okay. Others are saying that they're still stuck. Not sure if you have, if you've seen that with this, Royce.
No, that's never happened to us before.
Okay, so we have 2 or 3 that are stuck on the poll, and then it seems like quite a few others that are saying that it's okay.
Okay. Yeah, I'm not sure what to say.
And so for those that are still stuck on the poll, perhaps try popping out of the webinar and then popping back in. Worst case scenario, this will be recorded and posted online. But it seems as though a couple others are saying that they had similar and popped out and popped back in and are able to see the slides now.
Okay, great. Thank you, Apollo.
Thanks.
Yep. So the scalable wall function is something that's newer within our software, and this is really to address the accuracy issue. So as I was saying before, if you're doing, for instance, electronics model and it's very open and the pressure drop is more being driven by a lot of blunt bodies, capacitors, large chips, so forth, then you probably don't have a whole lot of sensitivity to your Y plus value. It's still going to give you a reasonable result. But if you're doing a external flow analysis, for instance, and you start refining the mesh more and more and more, you're going to eventually discover that your shear drag along this body is going to become less and less accurate. So one aspect of the scalable wall function is to try to address this issue. So as you look at the range that the Y plus is really valid for the scalable wall function, there is no minimum. You could add more and more mesh along the wall, and really what happens is it starts, in essence, ignoring the mesh that's below a specific value. Okay, still shares the various disadvantages, and it doesn't capture the laminar sublayer like newer models would actually fully capture the flow profile into the wall. And one aspect that becomes very important with heat exchangers is that the K-epsilon really does not capture high Prandtl number wall heat fluxes very well. And all that really means is liquids. So if you have like a liquid to air heat exchanger, you'll want to probably use one of our newer models. Either way, if you wanted to explore the intelligent wall function or the scalable wall function, you would have to go to the advanced settings under K-epsilon, and then there's a checkbox that says intelligent wall formulation. And once you enable that, you will be using this newer scalable wall function. So this is a newer technique within our code, and as you discover pros or cons to it, please let us know and support what you're finding. We will definitely find that interesting. So a newer turbulence model, which was actually added in the previous release, is the K-omega SST. So still a two-equation linear eddy viscosity model, but this is a hybrid. So as you may have noticed in the history slide, there was a model called K-omega. Well, that was discovered to actually solve the wall very, very accurately, but it had some deficiencies at the time when it initially came out that didn't capture the internal flows as well. So the K-omega SST was a blending of these two, as you might expect. Eventually someone will blend them, where the K-omega is solved along the wall, and then there's blending functions that actually bring the K-omega into the K-epsilon flow domain in the middle. Now these modeling techniques capture this near wall regions very accurately. It captures the flow domain, and really there's no minimum to what this Y plus can be. But this comes with some cons, of course, because you are going to need some more mesh probably along the wall to capture the accuracy of this layer. So in terms of pros, you can get much more accurate predictions and flow separations, which leads into the adverse pressure gradients, which helps you calculate more accurate drag values. As well as, since we're calculating the entire boundary layer, our heat flux calculations also improve on high Prandtl number flows. Now, going back to the wall considerations, the Y plus value, up to 100 is reasonable. If you were to talk to developers, they would say, ideally you'd want this down to 0.3. But we're finding that it can be very robust in the 10 to 100 range, so you don't need a very, very refined mesh along the wall. So here's just an example of a flow control device, and comparing the K-epsilon model with our ADV1, ADV5, as well as our SST K-omega model down below. And what was discovered was that the recirculation region, which goes along with the adverse pressure gradient, was barely captured downstream of the venturi. And even with ADV5, you can see it got a little bit more accurate. As we discuss, ADV5 is more accurate in general. But it really is not captured, and the pressure drop throughout the entire system until you turn on the K-omega turbulence models. And you can dramatically see how much larger that recirculation is. So, K-omega, really great model. And there's newer techniques to try to capture some other types of models you may need to need to do. So in terms of the detached eddy simulation, we talked about this before. This is a hybrid where the standard SST K-omega is solved in most of the flow domain, but where needed, the LES large eddy simulation is solved to capture these larger eddies. It's an unsteady model. That's what the U is before the RANs, so unsteady Reynolds average Navier-Stokes. So really running it transient is more appropriate. And you have these larger eddies, so you need to capture how they flow downstream. This is really going to be your most possible highest accuracy that we can provide inside of the simulation CFD, and works very well with high Reynolds external aerodynamics. Now, a lot of people will talk about using a large eddy simulation for their work, but this is going to be more efficient because it's going to solve LES where it needs and a more efficient model where it doesn't. In terms of cons, this is going to be much more intensive in terms of solver time when you compare SST as well as, in our next slide, the SES modeling approach. And in terms of mesh sensitivity, it can be very high, especially the transition from the wall into the core of the flow. And you'll need to really concentrate on having a smooth mesh. So my last point here is that, in my opinion, most of us shouldn't really be exploring the DES modeling approach. It ends up being very academic, but something that you can use and explore with. The newest modeling technique that we have is what's called the Scale Adaptive Simulation, or SAS. This is an extension of the DES, but there's actually there's a correction in there that basically makes it less mesh sensitive. So that's why I bring this up as more of a go-to if you need to capture the LES, or larger eddy flow structures. It's really designed to be transient as well, but it can still be used with a steady state simulation. In terms of cons, it's still computationally intensive, similar to the LES, and still requires a lot of refinement along the wall, but the sensitivity of the mesh growth from the wall into the flow domain isn't as sensitive. And this is really the state of the art. It's only a few years old, and for some of our models that we've done, it's shown to be very, very powerful. So in terms of other turbulence models, I can't have a turbulence discussion without bringing up some of the classics. Eddy viscosity, mixing length with low Reynolds K-epsilon. There's some other options you have available too. Eddy viscosity is very basic. It's a constant viscosity, effective viscosity throughout the entire model. And really the only time I use this model is sometimes with natural convection models, but more often than not, it's more of a troubleshooting tool. If you're getting diverged simulations very early in the solution, then maybe try turning on eddy viscosity. It's much more stable because it's not solving those two extra equations. And this will point to maybe that you have a meshing issue or something else, but at least gives you an idea that it's a turbulence issue, most likely. In reality, when you actually solve your model, the first 10 iterations are actually solved with the eddy viscosity turbulence model, just to improve stability for the first few iterations. Mixing length, most often I actually see this used in the lighting and external electronics cooling industry. It seems to work very well, and it's only adjusting the effective viscosity near to the wall, and then within the core it's just a constant viscosity value. The last option is the low Reynolds K-epsilon, and this solves no wall function. This is solving your classic K-epsilon all the way to the wall, and typical mesh enhancement requirements are like 5 to 15 layers, but really this isn't very accurate for the wall boundary layer. That's why the K-omega was really developed. So it's just not as accurate. It's more mesh intensive. So for most uses, I wouldn't really suggest to use this model. I would rather see users go to the K-omega SST instead. So this comes down to my last two slides I want to talk about, and we talked about a lot on turbulence models, of course, but now what do you do with these different options? So after talking with various people on our team, came away with sort of 3 levels I thought might be an interesting way to approach how people move forward. There's the basic. These are really the defaults within the software. So this is your K-epsilon with the standard wall formulation, where you need to potentially think about what your Y plus is depending on your application. Of course, our default values here are 3 layers with a layer factor of 0.45 or 45%, with no real gradation affecting how the distribution or biasing of that mesh close to the wall. And of course, in terms of the solver, we would suggest, depending on the application, advection scheme 1, 2, or 5, where 5 really we're finding is becoming more robust and more accurate for many users. And then we go to more of an intermediate level. This is not a whole lot of change. Maybe you start exploring the scalable wall function or intelligent wall formulation, and you don't need to make a whole lot of changes. Potentially you add more layers, so that's why we increase this to 5 layers, and otherwise just using A to B5 at this point. A lot of our newer turbulence models are tested for various advection schemes, but in terms of real development, they're designed around our newer numerical method, advection scheme 5. So that's why I highly suggest to start there when you look at these more intermediate and advanced. At the advanced level, I would suggest to go into the K-omega SST, and this is where we start adding in more layers, thicker layers, start skewing the boundary mesh closer to the wall, and potentially using a blending option, which is a newer checkbox inside of 2015 if you're doing external aero. This will help smoothen the mesh from the boundary layer elements into the core elements. As you probably see sometimes, the mesh transition can sometimes be very large from those boundary layers into the core, where you get these really large triangles very quickly. That will help smooth that transition. And if you're going to this advanced level, most likely that means to me that you're looking for accuracy. You're looking for fairly close test to CFD correlation. So I highly suggest to go to a tight convergence, or maybe even turn off convergence check entirely and go beyond convergence, do more of a manual assessment. But at least go to more of a tight convergence and wait for it to auto-stop. And lastly, using Advection Scheme 5 for sure with this modeling approach. So then where to use what? I could list a whole bunch of different industries, but there's going to be exceptions at all times. So you need to use your best judgment on what you're looking to do. You know, if you look at the pros and cons of the different turbulence models, that's where it points to what you need to think about. If you're doing an external aero of a car wing or an airfoil, for instance, then you definitely want to probably go with K-omega. Same with transient flows with a lot of critical wake structures, flow around a cylinder, for instance. Then that's when you start looking at the SST as well, but maybe start doing the SAS approach, where that will really capture the wake. Any liquid heat transfer and laminar to transitional, in other words, low Reynolds number flows, then definitely go with K-omega. But then from there, it's K-epsilon. I'm not here to tell you to change what you've been using probably for years, and it's probably been working great for you. So I'd definitely stick with K-epsilon if you've been successful. But maybe start looking at the intermediate and using the scalable wall function if you see a lot of mesh sensitivity, or you want to start using mesh adaptation in your workflow. So it's tried and true and produces reasonable results for many, many applications. So really that's what I wanted to present. I didn't want to go into too much in terms of what you see in the software. You know, that could be definitely another hangout in terms of, you know, talking about, you know, how it actually looks in results, you know, effective viscosity, effective conductivity, your TKE, TED values, and so forth. But if you want to talk about those values, definitely bring that up in the sidebar discussion, and we can you know, continue the conversation down those paths. So at this point, I'll open it up for the Q&A portion. So if Paulo or John, anybody else wants to chime in on what users are asking, I would appreciate that.
Yeah, we have a couple. One on mesh adaptation. Does mesh adaptation adjust turbulence parameters?
It does not adjust turbulence parameters, but it will adjust to a y plus value that you have set as a goal. Okay, so if you do mesh adaptation and you're shooting to have a y plus value of 10, then it will try to adjust that mesh enhancement to that value. Okay.
Hi, Royce. There's another here, basically a gentleman who's running external aero around a building.
Yep.
And he said it seems like he should use K-omega SST, which is probably true, but he's worried about the additional mesh count.
Yeah, so that is a definite concern because it's going to be a very large model around a building. Now, what I would suggest to him at that point is start off light. You know, go to 5 layers and just explore what your Y plus is to begin with. And you know, those larger buildings, if you really wanted to correctly mesh, is going to be a lot of mesh because it's a massive structure. So I would start off with a Y plus goal of 100 and go from there with SST and see how many layers it is. You know, 5 to 10. But I don't know if John or Apollo, if you had any other thoughts there, but that's where my first place would be. And you may need to run somewhat of a sensitivity there in terms of how much mesh.
Yeah, no, I'd agree with that.
Okay.
Yeah, same. Another guy, Gary Schultz, you probably know, has asked, would you be able to talk a little bit about the turbulent laminar ratio, what it does and where to change it?
Sure. Turb-lam ratio is basically a way to initialize the model. Okay. So if you were to look at, for instance, the mixing length model, that turb-lam ratio starts off at 1. Actually, I can go to the software, by the way. So what Gary asked was about basically this value right here, turb-lam ratio. And it starts off at 100, and it's adjustable for pretty much any model. And long term, this value is basically solved for. It only really affects the initialization of how much turbulence you have in the model to begin with. So it basically scales your effective viscosity, and if your viscosity is much, much higher, in other words, a really high turb-lam ratio, then you have a more viscous fluid, which slows down the simulation a little bit. So sometimes when, if you read our help system, it will say, maybe increase your turb-lam ratio to 1,000 or 10,000 when you have a jet blowing into a large space, for instance. And that's really, by increasing this value, you slow down the development of this jet and help maintain stability. So it goes along with solver control many times when you change this value. So just remember, what you make this value is corrected for long term when you use the K-epsilon and other modeling techniques. Now when you look at eddy viscosity, it defaults to 100, but it's actually held throughout in time. So many times if you're using eddy viscosity for electronics models, you should make that 1. Very similar to the mixing length modeling technique. So K-epsilon, we default this turb-lam to 100, and that's really done for stability. But sometimes, if a problem is taking a very long time to solve, and maybe adjusting that to 10 will actually help speed it up a little bit. Remember, it's adjusted for long term, but it does allow it to maybe start off closer to what it really is. Okay. Hopefully that answered Gary's question.
Yeah, I think so. I don't have any more present.
Okay.
There's one more that came in asking about SAS and scalar mixing.
Scalar mixing.
Yeah. So would you recommend SAS for high velocity scalar mixing?
Not sure if I really have an opinion. Like, in my perspective on scalar, you could, but
yeah, I'd say it would be dictated more on the flow solution than so much on the scalar mixing side. So think about what we've discussed here, what Royce has covered, and if SAS seems to be the most applicable or best suited for the flow solution, capturing the scalar mixing portion is just going to be a small piece. And then one other is if you wanted to actually go into what the Y plus value actually meant.
What it meant. So basically,
so what is a Y plus?
Yeah, so basically relates the velocity at the first node away from the wall and how that velocity should be compared to the expected boundary layer profile. So when you look at this, for instance, in this model, if we change to our Y plus value, okay, you'll see on this, this is our example car model. We can see the Y plus value throughout the flow domain, or along the wall. And if we start probing, this default mesh, I'm getting y plus values of around 1,000, so very, very large. And I would definitely want to start making more layers or making skinnier layers to try to reduce that value. So if you're to look at the velocity structure here along the wall, and maybe put a XY plot. Like right there. You can start to see, actually maybe I should look at the mesh, make sure I get outside. Yeah, there we go. You can see the first layer, second layer, and the third layer is probably right in here, and then the core mesh. So this y plus is a measurement of a non-dimensionalized distance to this node, in essence, and how that relates to the velocity. Now, if we made this a summary, for instance, and what I had done earlier, just in case the conversation went there, I ran this basic car model with our standard defaults, the IWF with K-epsilon, and the K-omega SST. So when we look at this, we start to see how the various models start changing this boundary layer and how it's captured. Now, I didn't change the number of layers for the various models, but we do see how this starts to capture more of the shape in transition into the core of the flow. Okay, so the SST model would be this orange line, the default would be this blue line followed by the intelligent wall formulation, which is actually this darker blue line. Okay. Anything you wanted to add there, Apollo?
No, it's
Okay.
covered basically what I would have typed out.
So one thing that we're going to be doing after this webinar is sending out a survey, of course, as we always do. And part of that is to talk about what else you'd want to talk about in terms of turbulence models. This is a conversation that comes up. And many of our users are not trained in CFD, they're trained on the job. And many of these smaller conversations never really come up when you're trying to learn to use the tool. So if there's other aspects you really want to discuss, that would be excellent to suggest. We're really trying to drive the content that we present based on your needs. So if you looked, for instance, at the polls that I asked earlier in terms of what people really do and people that are what kind of applications that you do, for instance, 42% brought in flow control, 24% electronics, and then some heat exchangers, AEC, and aerodynamics. So if most of our users are doing electronics and flow control, then maybe we'll start doing some examples of those models and how changing these turbulence models affect the results. One thing I was going to be thinking about doing later was taking more of an industrial automotive body and relating that to aerodynamics. So the about 10% of the people that attended today, they may be really excited to see that sort of discussion. In terms of turbulence models, about 50% of the people that were attending were looking at, they use K-epsilon, and then it goes into the laminar, and then lastly, some people have started exploring K-omega and some mixing lengths. So the laminar users are probably the passively cooled electronics designers. So that would make sense there. So thanks for everyone attending, and I look forward to talking to you in about a month.